Hello, I'm Seungwan from Hoyoung University. I'm glad to present our paper, and this work was done with Hoyoung Choi, Taehyung and Professor Kyungsik Han. I will briefly introduce our motivation. We explore self-supervised cross-modal alignment methods that leverage fine-grained details of the multimodal data. Following the guidelines defined in previous work, we consider pre-annotated image text pairs as positive, while all other pairs are considered negative. If we take the text from the first row as an anchor, we can see the alignment example on the right figure. When embedding the data, previous studies have focused on using transformer and global representations, such as the status token. However, in the figure on the left, as we can see in the first and second rows, fashion items are often very similar. Therefore, depending only on global representations makes it challenging for the model to distinguish between positive and hard negatives given anchor. Our goal is to improve the model's ability to learn how to effectively separate the positive and hard negatives in the embedding space by leveraging the fine-grained local features. So we propose a model, FashionFine, which consists of image and text encoders and a fusion encoder on top. The first module, MAA, plays a role in integrating global and local representations. Before integrating, this module learns how much weight to assign to the local features of the input image and text. We apply weight sharing when building the attention network, and this is to reflect the context of whether the input pair is positive or negative. Finally, we obtain the integrated representations through a weighted sum. The second module, HNM-F, helps the model focus on distinguishing between positive and hard negatives. Our HNM-F is based on contrast learning, so we calculate the relative similarity is as follows. We use soft labels to learn HNM-F, and the final loss function is as follows. By adding the focal loss term to the basic contrast loss, our loss can focus more on learning hard negative examples. The third module, C-CmA, helps the model to learn multi-level text features. First, we obtain the low-level feature from the 1D convolution and max pooling, and the high-level feature from the fashion symbol token. And then we obtain the multi-level text representation, and the loss function is as follows. In phase B, we perform hard negative sampling to carry out pre-trained tasks using fusion encoders. We set the input image and text as respective anchors and sampled one hard negative for each anchor. The two sampled hard negatives are used only for ITM, and the input positive pair is used for the three pre-trained tasks. To verify the effectiveness of FashionFine, we conducted performance evaluations on the two representative downstream tasks, cross-modal retriever and text-guided image retriever. Following prior work, we used the two public benchmarks, FashionGen and FashionIQ, and we fine-tune and evaluate our model on the two datasets, and the results showed that FashionFine is effective in achieving fine-grained cross-modal alignment. And we also ran an ablation study to see how much the proposed modules contribute. As you can see, all modules contribute to improved performance. And we observed the example-based results from the ablation study. Overall, we could observe that adding the HNM-F and C-CmA modules not only improved quantitative performance, but also improved the quality of the retrieval results. We also conducted an experiment to verify the applicability to foundation models. As you can see, the modules of FashionFine can be successfully applied to the BLIP, one of the foundation models. In summary, we demonstrated that leveraging local features improves the fine-grained cross-modal alignment and the boosting effect of hard negative mining with focal loss. Thank you for listening.